All right, in 4.3, we are going to take a look at the rules for logarithms. So these rules are really closely related to the rules for exponents. So, for example, remember when we were multiplying two exponential functions that had the same base, we would add the exponents. We're essentially going backwards here. If I am multiplying two things inside of a log, I can split that up into two different logs by adding them together. So, for example, right, if I've got log base 3 of 5x, right, these are being multiplied together, I can split this up into log base 3 of 5 plus log base 3 of x. Okay, now we're going to go both directions using these rules here in a minute. We're going to take a look at expressions like this, condensing them, and expressions like this, expanding them. Okay, the quotient rule, if I have two things being divided inside of a log, I can split that up into two separate logs by subtracting, like this. It does matter the order here, right? Subtraction, the order matters. So we would say the log of the numerator minus the log of the denominator. For example, if we've got log base 3 of 5 over x, we could split that up into log base 3 of 5 minus log base 3 of x. The power rule then says if I have an exponent, I can just bring that out front. I could rewrite this as r times log base a of m. Right? This is actually a form of the product rule. So, for example, if I've got log base 3 of x to the fourth power, that would just be the same as 4 times log base 3 of x. Right? I can, whenever I have an exponent on something, I can bring that out front of my log. So these are the big three rules that we're going to use. A couple others, if I've got log base a of m equal to log base a of n, that is the same thing, or that is only true if whatever's on the inside of the first log equals whatever's on the inside of the second log. Now, this right here, this is actually not a typo. If you ever see IFF, that stands for if and only if. Okay, that's something that you'll see as you get higher up in math classes. All right. This means that it works, this statement works in both directions. We can say m is equal to n if and only if the log base a of m equals the log base a of n, or we could say it in this direction. Log base a of m equals log base a of n if and only if m equals n. Right? The last one is just a special case of we could either think about it as rule 2 or 3. So here, if I've got log base a of 1 over m, I can use my quotient rule and write this as log base a of 1 minus log base a of m. But this, right, log base anything of 1 is just equal to 0 because this is saying a to what power equals 1? Well, a to the 0 power. So this would be 0 minus log base a of m. So I can just say that this is equal to negative log base a of m. Okay, but the big three are the first three: the product rule, the quotient rule, and the power rule. So let's take a look at some examples using those. Okay, first, let's take a condensed expression and expand it out as far as possible. So in this first example, we have a natural log of x minus 2 over x plus 3. I'm dividing, so I can split this up by taking the natural log of the numerator minus the natural log of the denominator. This is actually as far as I can expand this out. Okay, I no longer have any multiplication, division, or exponents inside of my logs. So this would be as far as I could expand this one out. All right, let's take a look at a few more. Okay, this one's got a couple of things happening. All right, now first, whenever we see a root, I want to think about this automatically as a fractional exponent. So the third root, remember, we can rewrite that as the 1/3 power. So first, before I even start expanding this, I'm going to rewrite this as x to the 1/3 times y to the 5th on the inside here. Now, the order that we would tackle things if we have multiple operations happening, we want to look at multiplication or division first. We want to expand that out and then worry about using the power rule. So here I'm multiplying these. I'm going to split this up into log base a of x to the 1/3 plus log base a of y to the 5th. And now I can take care of my exponents. Whenever I have exponents on something, I can bring those out front. So I can write this as 1/3 times log base a of x plus 5 times log base a of y. All right, and that's as far as I could expand that one out. Okay, let's do a few more examples here. Okay, this one, I see division, so I'm going to take care of that first. So this would become log base a of x minus log base a of x plus 7 squared. And then I can take care of this exponent. Right? I can bring this 2 out front here. Now, one thing that I do want to make sure that we understand is that I can only bring that exponent out if it is an exponent for everything that's on the inside of the log. If this were log base a of, if, for example, if we had x squared plus 7 like this inside of the log, I would not be able to bring this 2 out in front. I can only bring an exponent out in front of the log if that is an exponent for everything that is on the inside of the log. Okay? So this would be my final answer. I no longer have any multiplication, division, or exponents on the inside of my logarithm. All right? One more example like this. Okay? So first, I see a square root. I'm going to rewrite that before I do anything. So this will be natural log of 3x squared over 5 times y to the 1/2. Now, in this example, I have both multiplication and division. So I'm going to take care of the division first. Right? I'm going to rewrite this as natural log of the numerator minus natural log of the denominator. And now I can split these up because I have multiplication on the inside of each of these. So first I can say natural log of 3 plus natural log of x squared minus, now here we need to be careful because I'm subtracting everything now. So I want to put this in parentheses just to make sure that we understand we're subtracting natural log of 5, and then I'm multiplying, so I would say plus natural log of y to the 1/2. Right? I'm subtracting both of these things that are being added. Now we have one more thing we can do. I have exponents, so I can bring this 2 out front, and I can bring this y, or this 1/2 out front. So I can rewrite this as natural log of 3 plus natural log of x squared minus, and then in parentheses, whoops, I forgot what I was actually doing there. That 2 would come out front, all right? Then minus natural log of 5 plus, and I can bring this 1/2 power out front. So 1/2 times the natural log of y. Now, technically, we could distribute this negative sign to both of these, okay, but we can leave this answer as is, all right? So let's then take a look at going the other way. Let's condense our expressions. So we're given expanded forms. We want to condense these to a single logarithm. So here, one of the most important things we need to make sure of is that these have the same base. If these terms don't have the same base, I cannot combine them. These do, so we can combine them. If I'm adding two different logs together, I would multiply what's on the inside. So this would just become log base 2 of x times 5, or we could write that as 5x, and that would be it. In my next example, I have a coefficient here. So whenever I'm going in this direction, right, whenever I'm condensing, I want to take care of the exponents first, right? So any coefficients I want to bring up as an exponent. So let's rewrite this one first as log of x squared minus log of 3y. Okay, real quick side note, right? Remember, since we don't see a base here, these would all be base 10, right? So one final step here. Since I'm subtracting, I can combine these into a single log by dividing what's on the inside. So I can write this as x squared over 3y. All right. A couple more examples here. Okay, this one gets a little bit trickier. I have coefficients on both of these terms. So let's start by bringing those up as exponents. Okay, this 1/2 would apply to everything on the inside of the log here. So this would be log base 3 of x cubed plus log base 3 of 4x plus 3 to the 1/2 power. Now, I am perfectly okay with you leaving it to the 1/2 power, but sometimes in final answers of problems like this, you may see this written then as the square root of 4x plus 3, okay? So then one final step here. Since I am adding, I can combine these into a single log by multiplying what's on the inside. So x cubed times 4x plus 3 to the 1/2 power. All right, let's do one more example of condensing. Okay, so here, first, this 1/3, I can just think about distributing this to each term on the inside here. So I can rewrite this as 1/3 times the natural log of x minus 2/3 times the natural log of y plus 1/3 times 3 is just 1. So that would be plus the natural log of z. Then let's take care of our exponents. So I can bring this 1/3 up and write this as natural log of x to the 1/3 power minus natural log of y to the 2/3 power plus natural log of z. So then let's combine these using our multiplication and division ideas. So first, if we take a look at these, I'm dividing, right? If I'm subtracting two logs, I would combine those by dividing what's on the inside. So this would become x to the 1/3 over y to the 2/3. And then I would take this and multiply by z. So to finally combine these, I can write this as x to the 1/3 times z over y to the 2/3. So remember, whenever we're multiplying something, right, this would just be, if I'm multiplying what's on the inside, x to the 1/3 over y to the 2/3 times z over 1, and then we would multiply straight across. Okay, so this would be my final answer here. All right. Let's take a look at one other situation that we could solve problems using this idea. All right. First, okay, we're given this information, log base 4 of x equals 3, and log base 4 of y equals 5. So I can use the rules that we just talked about to get a numerical value for something like this. We can only plug in 3 though if I have log base 4 of x by itself. Same thing here. I can only plug in 5 if I have log base 4 of y by itself. So I would actually need to rewrite this. Since I'm dividing what's on the inside, I could rewrite this as log base 4 of y minus log base 4 of x. Now that I have these expressions by themselves, I can say, well, I know log base 4 of y is equal to 5 minus, and I know log base 4 of x is equal to 3. So based on the given information, this expression would just be equal to 2. All right. So let's try another example like that. So here again, the same information, but we want to split this up. So since I'm multiplying these expressions, I can write this as log base 4 of x squared plus log base 4 of y. Remember, when we're expanding, we want to take care of multiplication or division first, and then take care of the exponents. So finally now, I can say this would be 2 times log base 4 of x plus log base 4 of y. And I know that log base 4 of x is equal to 3, so this will be 2 times 3 plus log base 4 of y is equal to 5. So 6 plus 5 gets me 11 for this expression. All right, so just a small problem solving thing where we need to use our rules of logarithms. The next idea that I want to take a look at real quick is just the change of base formula. So the change of base formula lets me rewrite any logarithm using any base. So since our calculators have log base 10 buttons or common log buttons and natural log buttons, we can rewrite any log using this idea. So let me explain with an example. So if I've got log base 4 of 11, I could just rewrite that as log base 10 of 11 over log base 10 of 4. Or it would actually equal the exact same thing if I plugged in natural log of 11 over natural log of 4. Okay, so let's evaluate that on the calculator. Okay, so let's plug in log of 11 divided by log of 4, and we get 1.7297 or 1.730 if we round to 3 decimal places. Now, if I plug in natural log of 11 over natural log of 4, we actually get the exact same thing. Okay, this change of base formula lets me rewrite anything using log base 10 or log base e. So the answer here would be 1.730. Now, I do want to show you something else on the calculator here. Okay, the new programs in the TI-84s let you just calculate any log without using the change of base formula. So if you go into math, oops, there it is. Okay, and scroll all the way down to log base in the first option. It lets you actually just put in log base 4 of 11. Okay, so you can use a newer calculator to just compute logs like that without using the change of base formula. However, on a test, I may put in a question that you would have to understand the change of base formula. Okay, so know that you can just do this on the calculator. If you go to math and then scroll all the way down to log base, you can just put logs like this into the calculator. But also make sure that you understand the change of base formula. Okay, so let's do one more quick example. All right, if I've got log base square root of 3 of 123, I can rewrite that as log of 123 over the log of the square root of 3. Right? So log of 123 divided by log of the square root of 3 gets me this, 8.760. But again, if you go to math, scroll all the way down to log base, I can just put in log base square root of 3 of 123 and it will give me the exact same answer, 8.760. All right. The final idea that we want to take a look at is just a quick application. The exponential growth formula. This is a formula that is used to model lots of real world situations. Okay, this is actually just a rewriting of our PERT formula. Okay, where we said P was the principal amount of money that we started with. Well, here, if we want to apply this to other situations other than money, they just rewrite P as A sub 0, which means the initial amount of whatever we're talking about, times E raised to the KT power. Now, K really operates just as a rate in these scenarios, but sometimes we don't talk about it as a rate if we're talking about something else, exponentially increasing or decreasing. So let's take a look at an example dealing with population, right? So let's say that we're assuming an exponential growth model. So that's what this is called. This A amount equals A sub 0 times E to the KT power assumes an exponential growth model. So here we're saying we are assuming that the world population is about 7.8 billion in 2020. If the world adds about 100 million people in 2021, what is the rate of growth? Well, I want to use this formula, and if I'm solving for rate of growth, I'm going to be solving for k. So let's take this formula, a equals a sub 0 times e to the kt power, and let's take a look at what we know. So I know we're saying my initial amount is 7.8 billion. So a sub 0 is going to be 7.8 billion people times e to the, I'm solving for k, and my time, if I'm going from 2020 to 2021, that's just a time span of 1 year. So my t value is just going to be 1. Now, we're saying that I'm adding 100 million people. So what would my final amount be? Well, we need to think, this is in billions, this is in millions. 100 million would be 0.1 billion. So we could actually say this final amount in this situation would be 7.9 billion people. So now I just want to solve this equation for k. To do that, I'm going to divide both sides by 7.8. Right, so we'll have 7.9 over 7.8 equals just e to the 1 times k, or e to the k. And we looked at problems like this already, right? Now, once we get to this step, we can either think about this as just rewriting this as a log or taking the log of both sides. I would be using a natural log because my base is e. So this would be log base e, or natural log of 7.9 over 7.8 equals k. All right. So if we plug that into the calculator, natural log of 7.9 over 7.8, that gets me this rate of growth. Okay, so that's about 1.3%. All right, but let's write it as 0.01274. 274 equals k. So if we wanted to write that as a percentage, and usually we'll just leave it like this, but if we wanted to write it as a percentage, that would be 1.274%. Okay, so in this situation, that would be my rate of growth. Now, I do want to real quickly mention that when we're talking about population, usually we don't just use an exponential model. Okay, in this situation we did, but exponential growth, right, just says the growth is going to continue to keep growing faster and faster forever. This idea here of logistic growth is actually what they use to model most population situations. All right. Usually populations increase quickly to start, but then start to level out. Okay. This is because of a variety of factors, but usually just because resources limit how fast a population can grow or how big a population can grow. And if we look at our world population, that's actually already starting to happen, right? This uh, bluish green area is the world population, right? And up to here, this is the data from 2019, right? It looks like it's growing pretty rapidly, but it does actually already look like it's starting to level off. It doesn't look like it's following that exponential growth pattern anymore. And this purple line here shows us that the growth rate of the world population is decreasing. Right? It was over 2% in the late 60s, but by last year, it was just over 1%. So we're already seeing the world population start to follow that logistic growth model, right? For our mathematical purposes here, we are just going to use simplified versions and use this formula to model exponential growth. But I just wanted to show you that there is another model that's a little more accurate for most populations. Okay, so that is it for this video. The final question is going to pop up asking you what questions you have.